All right. Well, thanks all for being here. We're going to talk about file formats, assembly, big data, and all this kind of stuff. My name is Achille. I'm a co-founder of Dispatch.run and also a maintainer of a bunch of stuff in the Go ecosystem. And Parquet is a columnar file format that's become very popular in the big data space because you got all the features you want for doing efficient storing and querying of data, like encoding, compression, indexes, Bloom filters, all this stuff. And in 2021, I was working at Segment, and we had a lot of big data we wanted to keep in object store and being able to, query it efficiently. And unfortunately, all the packages at the time didn't meet our performance requirements, or had a lot of, questionable maintenance state. And so I thought to myself, how hard can it be to write a Parquet library? So let me tell you, it was really hard. Fortunately, I met a couple of friends from Polar Signals and Grafana Labs at the time who were looking for a similar solution. So I open sourced Parquet-go, and we created a little community of maintainers to develop and build a project. And you might ask, how did we make it fast? So for me, there were really two key choices that we made. One was the design of the high-level APIs that really enabled high performance. And the other one was just to write all the data crunching parts in assembly. And in Parquet-go, there's two core interfaces for reading and writing rows. And the key point here is that they work on arrays of rows. And because of this, we can amortize the cost of those interfaces over the length of those arrays. And that already gives you, very fast code. But then it spends all the CPU time in the innermost parts of the library, which are those that we've implemented as vectorized algorithms in assembly. So I'm going to go over a couple of the algorithms that we've built in. In Parquet, there's a lot of bit packing, right? Like if to do efficient encoding, just like take all your data and like put it in like less data. And there's this paper from Daniel Lemire that describes how to do bit packing of integers using vector instructions. So you can bit pack a bunch of integers into like a bunch of bits and then unpack them. I don't know if any of you have ever tried to implement a research paper. One thing I learned is it describes the high-level idea, but doesn't really go into the implementation details. So a lot of the difficulty here was reconciling theory with reality to make the whole thing work. For running encoding, Parquet does a lot of encoding the deltas between value instead of the values themselves. And this is because the deltas tend to be a lot smaller, so they can be bit packed into fewer values. However, this is really hard to parallelize with SIMD instructions because there's data dependencies between the items. But thankfully, there's research paper on the topic as well that we could use here. However, once again, we're dealing with real-world data here that might be corrupted, comes from the internet, we don't know. And so on top of like encoding, we also need to do validation. So we had to modify the reference algorithms a little bit to add validation on top of it. Oh, and this one is like a cool one as well. So there's an encoding in Parquet that's called byte stream splits. It's designed especially for floating value. And the idea is instead of like storing all your floats as an array, you kind of like reshuffle them to store all the first bytes, then all the second bytes, then all the third bytes, etc. And when you compress this, it compresses a lot better. And this is a perfect use case for scatter and gather instructions that allow us to work on non-contiguous area of memory. So basically with scatter, when you're encoding your floats, you're going to put all the bytes of your float in the right locations in the output buffer, and similarly when decoding with gather. All right, now on to the more advanced parts of Parquet-go. So we have a Bloom filter implementation in Parquet-go that is also optimized using AVX2. And this is because the split block filters of Parquet are 32 bytes, and that allows us to map those memory regions to YMM registers of AVX2. And as you can see in this benchmark, we reach almost 30 gigabyte per second when we're generating the Bloom filters. However, to put values in the filter, we must hash them first. So the hashing algorithm can become a bottleneck on this code path. But thankfully, we'll also have parallel implementation of those hashing algorithms. So there's a XX hash implementation in Parquet-go that works on multiple values at the same time, and it allows us to get to 1 to 2 billion hash per second, which is, to my knowledge, the only Parquet library that has this type of capability. All right, that was a little bit of an overview of all the optimizations that we put in the library, but there's a lot more, and especially there are some that I'm trying to contribute back to the rest of the Go ecosystem by putting them in the standard library, and especially this CL that I have open. So if anybody here has merge rights on this, we get up to like 60% boost on some of the benchmarks that there are. All right, to wrap it up, I want to thank all the contributors to Parquet-go who have been on this journey with me. This is one of the favorite projects that I maintain. And also, be generous with your open source maintainers. Hit that GitHub star button, and that's it. Thank you so much.